Section 4.1 is about maxima and minima points, and in this section we're looking at relative max and min. That just means we're higher or lower than the points around us. And to do this, we're going to look at the derivative, and we want to remember that the derivative measures both the slope of the tangent line and the rate of change of the function at any x value. That's instantaneous rates of change. And this will lead us right into our theorem 1 here. If f prime of x is bigger than 0, that means if the derivative is a positive number on an interval, then the original function must have been increasing. So if you have a positive derivative on an interval, then the original function must have been increasing. It must have been rising left to right. So we could write increasing. It could look kind of straight up like a line, or it could go up steadily. But if the derivative is positive, the original function was increasing. On the other hand, if f prime of x is less than 0 on an interval, then that interval where we get a negative derivative must have had a decreasing original function for the derivative to have come up negative. So decreasing or falling left to right could be falling in a straight line or falling kind of with a softer slope. If f prime of x, if the derivative equals 0, then the original function is constant. It's not increasing or decreasing. It's constant, which could look like a flat line, or it could look like it's at a soft peak. Would have a derivative of 0. Squeeze that in here. Soft peak. And we can draw what that looks like over here. It could look like the top of a maximum. That would have a slope of 0. Or the bottom of a relative minimum would have a slope of 0. So to determine where a function is increasing or decreasing, we're going to do 2 steps. The first step is to take the derivative and set it equal to 0, or figure out where f prime is undefined so that it's discontinuous. And then the second step is to test values between the x values that were 0 or undefined. And when we test these intervals between, which is going to be really making a sign chart, we want to remember that if we plug in a test value c and we get a positive derivative, the original function was increasing. Just reiterating this. And if we plug in and the derivative is negative, the original function f must have been decreasing on that interval. So with this, we get a definition, and that is that a critical number of a function is any number x in the domain of f such that f prime is 0 or f prime is undefined, meaning like the denominator is 0. So we're going to look at an example of this. We're just going to start off by finding the intervals where f of x equals x cubed is increasing and where it's decreasing. And that's going to lead us eventually into the relative maxima and minima. So our first step of our 2 steps is to always take the derivative and set it equal to 0. See where it's 0 or undefined. So my derivative of x cubed is 3x squared. And I'm going to take that derivative and set it equal to 0 and solve for x. So to get x by itself, the first thing I need to do is divide both sides by 3. So I'm going to take that derivative and divide it by 3. So x squared is going to be equal to 0 divided by 3. 0 divided by anything is 0. My next step to get x by itself would be to take the square root of both sides. So I'm going to take the square root over here, and I'm going to take plus or minus the square root of 0. Right? Because anytime you take the square root of a number, you need to do plus or minus that square root, because the square root of 25 could be positive or negative 5. So here we have plus or minus the square root of 0, which is kind of silly because the square root of 0 happens to be 0, which is neither positive or negative. So x could only be 0. That's the only critical number I get. Again, it's a critical number because it makes the derivative 0. The derivative of 3x squared is 0 anytime x is 0. My second step, after taking the derivative and setting it equal to 0, is to make a nice sign chart. So on my sign chart, I'm going to label my critical number. My critical number makes the derivative 0 or undefined. So my critical number is x is 0. And I'm just going to label that in here. This is my critical number. It made f prime 0. And I'm going to test numbers to the left and to the right to see if the derivative is positive or negative. That'll tell me whether the original function was increasing or decreasing. So I'm going to test a number to the left of 0. Maybe I'll plug in -1. I'm going to circle it. It's a random test value that I made up. And we're going to plug it into our derivative. Every time you always plug into a derivative on your sign chart. So I'm going to plug in 3 times -1 squared. And we want to remember PEMDAS. We have to do -1 squared first, exponents first. So -1 squared is 1 times 3 is going to be a positive number. So the value you get out isn't super important. The sign of it is. And this is definitely going to be a positive number. In fact, it's positive 3. So if our derivative is positive, that means before critical number we were increasing. A random test value to the right of 0, well, I could just plug in a +1 and see the sign of the derivative. So plug into the derivative again. I'm going to plug in 3 times 1 squared. Well, 1 squared is 1 times 3 is 3. The value doesn't matter. The sign of it does. I get a positive value out, so my slope must have been positive. So I'm going to interpret my answers. So I want the intervals where I'm increasing and decreasing is what I'm asked for in this problem. So I'm increasing before 0 and after 0. So I'm increasing -infinity to 0, union 0 to infinity. And the reason why I don't just write I'm increasing -infinity to positive infinity is because I don't have a positive derivative at 0. My derivative at 0 is 0. I'm constant there. So I'm not actually increasing there. But I am increasing before and after. And then my intervals where I'm decreasing, there are simply none. There are no x values I could plug in and get a negative derivative out. Which makes sense because my derivative is 3x squared. Plug in any number there and it's going to end up being positive. So the derivative isn't ever going to be negative, so I won't have any decreasing intervals.